So the new unit that we're doing is studying functions. So the first thing we're going to do is just go back and review all of the different parent functions that we've learned in Math 3. Hopefully you've been introduced to all of these, and just make sure that they're not completely brand new and that we can graph them on a graphing calculator since we're not using Desmos in this class. So the first one is an absolute value function. So we're going to hit y equals, let me just clear mine real quick. We're going to hit y equals, and then to get to the absolute value function on the calculator, you hit the math button. And you go over to number, and you press number 1 for absolute value. And it'll give you those vertical lines. This is that perfect V-shape graph. So we hit the graph button so we can see the perfect V-shape graph. And then if you want to get the points from the table, you hit second graph, and then there's your table. So from here, you would hit the math button, and you would go over to number and press enter. Yep, press 1 or press enter. And then you can hit graph to see the picture, or second graph to see the table. So the values that we'll use is we'll put 0, 0 right in the middle. I just put X. I'm just typing in the parent graph right here. So we've got 0, 0 is the middle point, and then above that, -1, 1, -2, 2. So just like we did the unit before last when we were graphing quadratics, whenever we graph absolute value graphs, we're going to look for the vertex first. And then after we find the vertex, we're just going to do a couple points to the left, a couple points to the right, and then we'll make sure that from there we have the whole V-shaped graph. So I've got 0, 0, 1, 1, 2, 2. -1, 1, -2, 2. And then these graphs are really easy to draw. They literally just go over 1, up 1 on each side, like all the way. So if you wanted more points, it'd be really easy to get more of them. They just look like that. So that like perfect V-shaped graph. And the vertex you can get from the equation. If it said minus a number, you would just do the opposite sign. So if it said minus h, then positive h is what would be part of the vertex. And then you would take exactly whatever the number on the end was. So opposite sign for the h value, exactly the same sign for the k value. And that's how it works whenever you find the vertex. Or if a graph doesn't have a vertex, we would call it a locator point instead. It's like the middle point, and you find it the same way. Then it'd be negative. All right, quadratic. So here we're going to go to y equals x squared. Somebody did not put their phone on Do Not Disturb. Ask me how I know. It's ringing. This is very distracting. Oh no, it's a whole pile of phones. Okay. All right, so y equals x squared. We're going to go ahead and hit graph. This is not a V-shaped graph, it's a U-shaped graph. So here I'm going to do second graph, get the table. Again, 0, 0 is right in the middle. This is the vertex. And then we have -1, 1, -2, 4, and then 1, 1, 2, 4. And this makes a U instead of a V. So we got 0, 0, 1, 1, 2, 4. And we can say that we find the vertex the same way. Vertex is HK. Next, we have a square root graph. So I'll go on to y equals. Square root, how do we get that on our calculator? Yeah, so hit the second and then hit the x squared button. And you can tell that's what you're doing because it's the blue above the x squared button that is where the square root is. So blue and then x squared. And press the x. So square root. And then if you hit graph, you can see it. And second graph to get the points. So here, we don't call it a vertex because a vertex is only if you go down and come up again or go up and go down again. But 0, 0 is kind of like the starting point of the graph. So we're not going to plug in any negative values, right? If you take the square root of a negative number, you get an error message because you can't technically square root a negative. You get imaginary numbers, not real ones. So I'm going to put 0, 0 to start with. And then when I put the rest of my table, I don't like to put down the numbers where I'm square rooting something that gives me a decimal. So I only put the perfect square roots in my table, like the square root of 1 is 1. And then I don't put 2, I don't put 3, I just put 4 next. The square root of 4 is 2. And then what would I put after that? I'd go all the way down to 9. I'd skip all those decimals, and then I'd say the square root of 9 is 3. I'm running out of space after that, not in the table, I'm running out of space on the graph. But what would I have next in my table if I had space on the graph? 16 would be my next point. Yeah. So I've got 0, 0, 1, 1, 4, 2, and then 9, 3, and that's about as far as I go. So in most graphs, I would find the vertex or the starting point, and then do a couple points to the left, a couple points to the right. The square root graph is an exception to that because it doesn't go to the left. It only goes one direction. So we're going to say, I'm going to call this the locator point. Different math teachers call that different things. I don't know that there's an official name for it, but I call it the locator point. And again, you find it the same way. You still use H and K. Locator point is still HK. Say that again? It still changes, yep. It's very consistent, yeah. Okay, let's do a cubic. So x to the third. Y equals x, and then to get to the third, we're going to use this button right here. People call it the caret button. I don't know why. Maybe because it looks like the top of a caret. I don't know. So we do this right here, caret, and then you can put any exponent you want. So x to the third. Everyone get that? Okay. And then we're going to hit graph. And then second graph, so we can see more points. So I'm going to go back and I'm going to look for that. It's not a vertex because a vertex is where you go up and come down again. So here we're going to call it a locator point again. 0, 0 is going to be right in the middle as the locator point. And then we've got -1, -1, and then -2, -8, +1, +1, +2, +8. So this right here in the middle, here's the locator point. And then since this graph goes in both directions, then I'm going to find 2 points to the left, 2 points to the right whenever I graph these. So I've got 0, 0, -1, -1, -2, -8, +1, +1, positive 2, positive 8. And these ones look like half of a U shape going up and half of a U shape going down. There, something like that. And just like all of the other ones, if you want to find the locator point, it's just HK. Do you guys remember studying all of these from Math 3? Yes. These are all familiar? Okay. Alrighty. Carly. Okay, next one is cube root. I'm going to show you guys two different ways to plug in a cube root. So the first way is to get to the cube root specifically. So if we press clear, we can just hit the math button. And then number 4 is to do a cube root specifically. But it's kind of nice to know how to do any other type of root, a 4th root, a 5th root, a 6th root, a 7th root, if you needed to do another type of root. So we're going to go back to y equals, and we're going to do a cube root the other way if you wanted to do another type of root as well. So if you wanted to do a different type of root, we would press 3 first. So if you were doing a 5th root, you would press a 5. If you were doing a 7th root, you would press a 7. You would have to press the type of root you wanted to do before you did this, okay? So 3rd root, so we're going to press a 3, and then you hit the math button, and then you go to option 5. So what option 5 does is it takes the number that you just pressed and it puts it in for the little X right there. And that's how you do any other type of root. So if I press 5 now, it took the 3 and it pulled it in for that X. Does that make sense? So in that menu, it's not using X as a variable, it's using X as a placeholder for where they're going to put the number in for the root. Make sense? Okay, so you can either use option 4 or option 5, it doesn't matter. So cube root of X, and we'll go ahead and graph. So this is just a cubic graph that has kind of been like spun around, flipped on its side. And so we're going to do second graph to look at the table. Again, we're going to have 0, 0 right in the middle. There's our locator point. And then kind of like we did with the square root graph, I'm only going to choose values to put in the table that are easy to cube root. So -1 is easy to cube root, and negatives are not the same within cube roots as they are within square roots. So within a square root, you can't square root a negative because you would be saying what number times itself is a negative number, and that's not possible. You can't have two numbers multiplied together equaling a negative. That's why it doesn't work. Now, with a cube root, you would be saying what number times itself 3 times equals a negative. That is possible because a negative times a negative times a negative is what? A negative. So that's possible. So here, if you said the cube root of -1 is what? Well, it's -1 because -1 times -1 times -1 is -1. So that works. So here, when I look for other values in the table, I'm going to skip anything that's a decimal, and I'm going to go back up. And if you cube root -8, you would say what multiplied by itself 3 times is -8? And the answer is -2. -2 times -2 times -2 is -8. So the cube root of -8 is -2. And you'll notice that's really similar to the cubic table that we had. It's the inverse of it because cubes and cube roots are opposites of each other. So these are the two tables that are kind of funky, the cube roots and the square roots. Okay, so I'm going to go ahead and graph those. 0, 0, 1, 1, -1, -1, and then 8, 2, -8, -2, and then I think of just a U shape kind of on its side. And again, we've got the locator point just like before. All right, and I left the weird graphs for the end. So for these last two graphs, they do not have locator points. Neither one of them do. So for these last two graphs, we graph them based on other things. So for this graph, the interesting thing is that while it doesn't have a locator point, it has like locator asymptotes. Does anyone remember what an asymptote is from Math 3? Yes. Kind of. A number that it can't go past. Yeah. And is it a specific number? Is it like a point on the graph? It's a line. Yeah, an asymptote. So when you get into more advanced math, you start to learn a more advanced definition. But when you first learn about asymptotes, most teachers will say it's an imaginary line on the graph. So you don't actually graph it and say this would show up on the graph. It's an imaginary line where the curve, whatever you're graphing, will not cross it. That's like the basic definition when you first get started learning about them. It's an imaginary line on the graph where the graph will not cross that line. So while this does not have a vertex or a locator point, it does have two asymptotes that have to do with the h value and with the k value. So we're going to have these same two numbers. Now, which of these has to do with left and right, the h or the k? The h. The h has to do with left and right. So if we think about which value is going to divide the picture from the left to the right, it's going to be a vertical line is going to divide the picture from left to right. Does that make sense? A vertical line would divide the picture from left to right. So we're going to say VA, this means vertical asymptote. And I'm going to write the word asymptote off to the side because that's new for you guys. The P is silent. Asymptote. That's how you spell that word, asymptote. So vertical asymptote is going to be x equals h. And you'll notice, just like it's been consistent the whole way through, the h is the opposite sign. So there's going to be a vertical line that we can't cross at the h value. And then there's going to be a horizontal line that divides the graph in half from top to bottom. So a vertical line that divides the graph in half from left to right using the x coordinate. A horizontal line using the y coordinate that divides the graph in half from top to bottom. And this is going to be y equals k. So even though we don't have a vertex or a locator point, we're actually still going to have a place where those two vertical line and horizontal lines cross, and it's going to be kind of that middle point of the graph. So here's how we draw those asymptotes. We say a vertical asymptote would be at x equals h, and in the case of this graph, it's going to be 0 because we're not going to have any values there. You can see that if 1 over x is my parent graph, there's just no number there for the h. And we always draw them on the graph as dotted lines, and that shows the person who's looking at your paper that you recognize there's an asymptote there, even though it's imaginary. Like, yes, I'm aware that these graphs do have that. Okay, so there's our vertical asymptote. I'm going to label this. I'm going to say this is x equals h. And then I'm going to graph my horizontal asymptote over here. And this is y equals k. Now, this is either going to feel familiar to you if you got to this point in Math 3, or if you guys didn't get to this in Math 3, this is going to be completely brand new. So for those of you who had Boyette, did you guys get to this or not get to this? This is brand new? This is brand new? Okay. All right, so let's go ahead and graph this. We're going to graph 1 divided by x. Now, you can type this in 2 different ways, and I want to show you how it impacts the table depending on how you type it, okay? So if you type this in as 1 divided by x, let's look at the table. So when we graph it, it's going to look the same. See, it graphs like that. And then if you look at the table, see what your table looks like. Let's get to 0, 0. Let's get to the middle. Okay, so there's the table. Everyone see the table? Okay, let's go back. Now, if you graph it as a fraction, you can do alpha y equals and graph it as 1 over x. And now if you hit second graph, what happened to your table? It's fractions. So if you plug a function in as a fraction, your values are going to be in fractions. If you type a function in as division, your values for your tables are going to be in decimals. Does that make sense? So it's going to be kind of dependent on what you would like to have it show up as. So for us right now, how would you guys like to type this in? Fractions? We want fractions? Okay. So let's go ahead and write down these. So if we plug in 0, we get an error message. And that's because this is where our vertical asymptote is. That's why we're getting an error message. It's where our vertical asymptote is. All right, but then for the other points, we have -1, -1. And now I'm not going to be worried about the rest of them because if I look for a whole number, do you guys see how I'm not going to find it? See how those fractions just keep getting worse? Yeah, so I'm not going to look for another whole number because I know it's not going to happen. I'm just going to leave the point -2 for the x coordinate and -1/2 for the y coordinate. And then on this side, +1, +1, +2, +1/2. Okay. So I've got -1, -1, -2, -1/2, +1, +1, +2, +1/2. Now, the way that asymptotes work is the line gets really, really close. The curve gets really, really close to the asymptote, but it doesn't cross the asymptote. So I'm going to start here. And then I'm just going to show that my curve gets really close to it. Draw an arrow. And then I'm going to show that my curve gets really close to it up here. Draw an arrow. Like that. Same thing over here. My curve gets really close to it. Draw an arrow. Curve gets really close to it, draw an arrow. So I think of these as looking kind of like the corner of a table or the corner of a desk. So not a 90-degree angle, right? It's kind of a rounded corner. All right, how are your brains doing with that? Okay. All right, for the next one, we have exponential graphs. Exponential graphs, those do not have a vertex either. They also, here I wrote that this is the base. And so the base could be different numbers. It could be y equals, we're going to write this down here. It could be y equals 2 to the x. It could be y equals 3 to the x. It could be y equals 4 to the x. It could be y equals 5 to the x, 6 to the x. There's actually one that's y equals e to the x. Does anyone know what the math number e is? It's kind of like pi, but it's a different one. It's a different special math number. Anyone know what it is? Doesn't have to do with 0. It's after a mathematician. His name is pronounced Euler, but it's spelled with an E. It's E-U-L-E-R. It's not Euler. That's how you mispronounce it. His name is Euler. It's Euler's number. It's on your calculator, actually. So you can see it right above the ln button, e to the x, right above the ln button. It's a special number on your calculator. There's another place that it's on your calculator. It's right over here above the division button. So right here, E, if you type that in, 2.718. It's a special number, E. So E to the x is very common as well with exponential. So over here when I did a capital B, it was just to say that that's a base. We could do any different type of base, okay? What base would you guys like to do for the parent graph? It doesn't matter which one we choose, we just have to choose one. 2. Let's do a base of 2. Okay, so we're going to do y equals 2 to the x over here. So we'll type in 2 to the x, and we'll graph it. Go ahead and hit graph. Okay, now I'm going to show you guys on mine, you can leave your guys as the same. I'm going to show you guys on mine a few different graphs so you can see what's happening. So we had 2 to the x where I'm adding 3 to the x. Okay, so do you guys see how 3 to the x just made the graph steeper? Okay, so it grew more quickly. Okay, let's try 4 to the x. 4 to the x. Okay, it grows even more quickly. Now let's go ahead and look at the table of values. So if I look here, when I plug in higher numbers for the exponent, we know that graphs that grow exponentially, it makes sense. The higher the exponent, the bigger the number is, right? All right, now if we think about what happens with exponents, the lower the exponent, like if I get negative numbers, that means that I start to get decimals or I start to get fractions. There is no point where I can plug in a number where I'm actually going to get a negative output. The number is never actually going to be negative. It's just going to be a fraction that is very, very small. Okay? There's no number you can plug in as an exponent that would make a number turn negative. Okay? Because negative exponents take a number and they just turn it into a fraction. That's all they do. So 3 to the second power is 9. 3 to the negative second power is 1/9. 4 to the third power is 64. 4 to the negative third power is 1/64. Does that make sense? So no matter what I plug in for an exponent, there's no way to make it become a negative number. There's no way to make it zero out either. Does anyone remember what anything to the 0 power is? It's 1. So there's no way to make it become 0. There's no way to make it become negative. So if you were to scroll this forever, we're getting some scientific notation in here because our calculator has too many decimals to be able to show them all on the screen. But we're never actually going to find one that has a negative value. We're never going to find one that has 0 either. So what we're going to do over here is we're going to draw that there is a horizontal asymptote at 0. And we're also going to fix my typo. I have a typo right here. The plus k I put in the exponent right here, and it should not be in the exponent. So put plus k and make it bigger. It should not be in the exponent. And then we're going to write the horizontal asymptote is y equals k. Okay, so here's something I want you to notice. For all of these graphs, if you plug in 0, if you have 2 to the x, 3 to the x, or 4 to the x, if you plug in 0, what value do you get? You get 1. So if you plug in 0, actually here, we'll do this. No, I'll do that. If you plug in 0, you get 1. That's always the case. Okay? Now, if you're doing a 2 to the x graph, if you plug in 1, you get 2. If you're doing a 3 to the x graph, if you plug in 1, you get 3. If you're doing a 4 to the x graph, if you plug in 1, you get 4. So how do you think it works? If you plug in 1, what do you get? You get whatever the base number is. So if you plug in 0, you get 1. If you plug in 1, you get the base. That's how it's always going to work. So in this situation, we had 0, 1, 1, and then 2. Does that make sense? 0, 1, 1, 2. Okay. So 0, 1, 1, 2. And then typically most people would say in that case, if you can graph the asymptote, you can graph those 2 points. That's enough for you to graph an exponential graph. Typically, that's all we would ask you to graph for an exponential. And then you can look at the graph and just make sure that you have the right kind of shape. So on the left side, you're just going to follow it along the asymptote right there. And then on the right side, you just know that it grows really fast. Okay. How are your brains so far going through all of these different graphs? Okay. Are we going to lose these notes? No, we're going to save these notes because they have really important information. Okay, for the transformations, this should be old news. So if the a value is negative, the graph has been reflected over the x-axis. That's old news. We've done that before. If the size of the number is less than 1, it's a vertical compression. If the size of the number is bigger than 1, it's a vertical stretch. We know that, right? I'm skipping B for a second. We know that if h is negative, the graph shifts to the right. If h is positive, it shifts to the left. That's familiar? If k is negative, the graph goes down. If k is positive, the graph goes up. We all know that, right? The part that is new, that the first unit when we did this, a lot of people missed questions on, was the b value because you didn't learn about it in Math 3. It is new to Math 4. And we have to be really careful about looking at the inside of the function. So for exponential, that's the exponent. For rational, that's the bottom of the fraction. For cube root, that's the inside of the radical sign. You have to make sure that you factor the inside part of the function, because now we can't just look at the inside and see exactly what it's saying. We have to make sure it's in the factored form. And I'd say like 2/3 of you guys were so used to Math 3, you just automatically did whatever it looked like, and you missed this transformation. So the inside, kind of like the h value, is the opposite of what you would think. But it has to be in factored form. Okay, so let's go ahead and flip the page. We're going to start looking at these other examples. So, of course, the first example where I said transformations, I actually didn't have one of these that needed to be factored. So let's look at example 4 to begin with. So if we look at this one, y equals negative in the front, the inside of the radical can be factored. How can it be factored? Negative x minus 3. You can take the negative out. And once you factor out the negative, what's left over? X plus 3. So the 6 you don't use because it's outside of the radical, yeah. So you have to do this to be able to correctly see what the transformations are. Okay, so if we look back at the previous page, for the b value inside, if that is negative, the graph has been reflected over the y-axis. So it's a different type of reflection than the negative meant before. If the b is a smaller value, then it's a horizontal stretch, so that's opposite of what we're used to. If it's a bigger value, then it's a horizontal compression. It's exactly the opposite of what we've been used to before from Math 3. Okay, so that's something we have to watch out for. Okay, so if we were to look at this one, what are the transformations? We got the negative in the front. The negative in the front?
Oh, no. I thought you were just naming out the transformations.
So what's the negative in the front? Which way? So reflect over x. What's this negative? Reflect over y. So reflect over x, reflect over y. Left 3, up 6. Okay. Let's go back to example 3 so we can start at the beginning. So this one has an exponential graph. So since there's an exponential graph, I'm going to circle this part right here. This is really important. If there's an exponential graph right here, that means that we have a horizontal asymptote at y equals -3. So I'm going to draw this line in here, and the reason that that is important is if there's an asymptote at -3, it means that the graph is not crossing -3. It's getting really close to -3, but it's not going to cross -3. And that's going to make a difference when I find the range. Okay? All right, so for the transformations, what do I have? There's a negative in the front. Okay, reflect over x. Down 3. One more transformation. And not right 4, left 4. So it's always the opposite of what it looks like. So left 4. Okay. The exponent is like the inside of the function. Okay. We already saw the transformations for this one. Now this one, if you look at the inside of the function, what would the inside of the function be? But it's not factored. So what would we have to do to the inside of the function? Think about taking out the 2. So we would want to think of this as y equals 3. We'd want to factor out the inside, take the 2 out, and then x plus 4. Okay, so what would the transformations be for this one? Vertical stretch 3. Horizontal compression. See how it looks like a stretch? So it's the opposite. So vertical stretch of 3, horizontal compression. And if you wanted to say a horizontal compression of what? You would say a horizontal compression of 1/2. So you say kind of like the opposite, like the reciprocal number or like the inverse. So vertical stretch of 3, horizontal compression of 1/2. What else? Left 4, and then down 1. Okay. Do you guys see how those transformations are working? So the common mistake that I found in Unit 1 is that students were saying left 8. Is left 8 correct? No, because you got to factor the inside. Okay, let's flip the page and look at the other examples. All right, what transformations do we see on this one? Is it vertical or horizontal? Vertical. How do you know it's vertical, not horizontal? Because it's outside. So this is outside of the parentheses. So this is a vertical compression, okay? And left 2 and up 1. Okay. The exponent, what does the exponent tell you? Because the exponent does mean something, but it's not a transformation. It tells you what kind of graph it is. it tells you it's a cubic graph. So it tells you that the shape of the graph is going to be this shape instead of a U shape or a V shape or one of the rationals. It tells you what it's going to be. Okay, so what I'm going to do is I'm going to leave the rest of these notes for tomorrow, and I'm going to give you guys the assignment and have you guys just do the portion of the assignment where you are writing down the transformations and writing down the graphs, sketching the graphs from your calculator. Does that sound reasonable? We can do that? Okay, so let me get these hole punched and handed out.